Hi everybody, thanks for your time already. I'm Dimitri Geskus, CTO at Chilas. At Chilas we make some ultra narrow line width swap source lasers. Well, actually we started off with having simple lasers, and they are based on chip technology. So what we basically do to make these lasers is we glue a glassy photonic chip, silicon nitride in this case, feedback chip, to indium phosphide gain section. And here the indium phosphide gain section makes the laser alive. So it is the amplifier of the cavity, and the tunable filter is feeding back the laser light there. We employ two rings there to tune the wavelength, and we can exploit therefore the full gain bandwidth of the indium phosphide gain section. Well, you see in the right-hand graph of this animation that the laser locks to one of the reflected spectral lines, and it suppresses nicely the side modes, so you get a very pure color of light out of these lasers. The line width is very, very narrow, so very pure colors, and the scanning range is extremely large. It took us a few years, but we managed to fully control these chips, and well, this is on the background that we get high-power tunable narrow-linewidth lasers, and with the new product, the Chilas Comet, we demonstrate that we stitch all these wavelengths nicely together, and then we get a swept source. This is our product portfolio. We do this trick at several wavelengths. We've got a fixed wavelength application which provides very narrow line width and ultra low noise spectrum there. For quantum applications, we've got the 100 nanometer tunable laser, which can be addressed to any wavelength within 1500 and 1600 nanometers. And here in this presentation, we zoom in on our swept source, which we now demonstrate for 40 nanometers. That sweeps over 40 nanometers continuous wave and delivers in 1 second a 13 dBm of flat output power, almost flat. It's a nice compact driver. To do this effort, you need dedicated electronics. So we developed an electronic driver with a nice interface there. At this moment, there is a 4 picometer grid programmed into this thing, but it can be customized to any wavelength schematic you want to have there. And yeah, it gives it 20 milliwatts of output power, and it's a nice small form. Over here, you see the output power versus the wavelength. Here you see the challenge we are facing. We have to tune some three resonators synchronized in a synchronized manner that gives a little bit of power fluctuation. And in this first variant, we've got some 30% power variation. But the nice thing with this swept source is there's no mechanics inside there. So from sweep to sweep, you have the exact same footprint over months of operation time. And that gives you a lot of feedback control to embed this laser into your application and compensate for any wavelength to wavelength power fluctuations. To demonstrate the wavelength agility, we made a small setup in our lab, and we take our swept source and we put a fiber splitter there together, and we take one constant power into a photodiode, and then the other branch of power is fed through an absorption line. And Caetano showed nicely what happens with water. You get some of the colors of light will be absorbed. Well, in a gas absorption cell, these lines are very fine and very hard to resolve. So you need typically a tunable laser to resolve these narrow vibration absorption lines of the gas. And we put the output on the oscilloscope. So in the result, we see in 1 second, we see all the absorption lines of this gas cell, also used for laser reference there, nicely resolved. And we expect also to see this fingerprint of this gas cell in our screen. And when you put them next to each other, you see it's perfectly identical. And we resolve all the absorption lines in 1 single second. And from scan to scan, it's always repeatable. It's the same thing going on. Well, we also get a lot of questions for what is the accuracy then? Well, At this moment, we have the scan calibrated for 4 picometers resolution. And if we zoom in on one absorption line, we see this 4 picometer step size nicely back into the result spectrum. In between the 2 points, the laser is scanning freely from one wavelength to the other wavelength. So the wavelength is not linear there. And in the next development, we will interpolate this data point to connect the lines nicely linear. But you see that this absorption line is very nicely resolved. There's a small offset, and that's probably caused by delay in synchronization, etc. Well, we also get a lot of requests for people making photonic chips. Typically, when you want to make a photonic chip, you put ring resonators on there or other aspects there. We also at Chilas exploit photonic chips. So we typically also have to test our own devices. And in our devices, there's a ring resonator. We look into the ring resonator, light going in and light going out. We get a high Q, very small spectral drop response in the output. And using our laser, we resolve the drop response into a graph, which we can monitor almost at video rates. In this example, we tune only over 1.7 nanometer subsection, and then the refresh rate is almost 24 Hertz. And we see nicely a video. While recording this video, this measurement, we tune the device in the test. And what you get in the end is that on the back side, you see the constant power in the blue curve, and in the red curve, that's the tuned ring response, which we are monitoring at the moment. You see there's a little bit of jitter, of noise on the power level from wavelength A scanning to wavelength B at 24 Hertz. And we scan the device in the test which we want to monitor with some sequence to show that the laser is hitting all the wavelengths. For the technical details here, you see over a regular pattern of nicks in the output power. Well, the laser actually stitches the motor-free tuning ranges nicely together, and every time it stitches, it takes about 200 microseconds to hit on the next mode and continues tune to the next wavelength. So you see no distortion of the spectral feature we are observing here. And it does this trick for the full 40 nanometers scan range. The thing is nice and compact, ready for use in your lab. There is a control board to interface it to power up and to a USB port for Python coding or LabVIEW interfacing. There's a simple serial command line in there, and there is also analog input and output to synchronize the swept source to your application to make nice graphs. There is also here on the top, there's a modulation input that's being evaluated at the moment, and that would be a very nice feature if you want to do some FMCW or LiDAR application with this data. Well, in the applications, it's a wide set of applications. I think you all have a laser in your laboratory somewhere hovering around, but this laser combines a very narrow line width, 1 kilohertz intrinsic line width of the laser with a wide tuning range. And that makes spectroscopy of optical Fourier tomography, fiber grading sensors, terahertz generations, LiDAR, photonic device testing, what we saw in the video, or any being a source for optical spectrum analyzers, you name it. We get requests from all these fields to use our lasers and to evaluate them. So if you have any questions, technical, or you want to buy it, please scan the code, contact me or info@chilas.bv, and then we'll bring you up light in your lab. Thanks a lot.